Hi, I am Dr. Global Enigmas, specializing in exploring mysteries around the world, analyzing mysterious phenomena beyond the limits of science, inspiring deep thoughts about the universe and life. Welcome to today's video. Today we are going to discuss
British theoretical physicist Stephen Hawking.
Where do we come from? Does ET civilization exist? How did the universe and everything begin? What is the meaning behind it all? Who designed all of this? We seem to always be troubled by these questions and unable to find answers. Stephen William Hawking, hailed as the greatest physicist since Einstein, the greatest physicist of humanity. Listen to how he thought about these questions. Hawking, at the age of 21 years old, in the prime of his life, contracted motor neurone disease, leading to total paralysis, and only 3 fingers could move. But even so, he still, with astonishing willpower, in the field of cosmology, especially in the theory of black holes, achieved great accomplishments. More importantly, Hawking has been dedicated to simplifying profound scientific theories to make our universe more understandable to a wider audience. Before Hawking's passing, he provided his own answers to 10 ultimate questions about the universe. He provided his own answers and compiled them into a book. It's called Brief Answers to the Big Questions. In this book, Hawking organized his thoughts on extraterrestrial life, black holes, time travel, predicting the future, God, and other ultimate questions. Today, let's listen to how this most outstanding physicist of modern humanity, how to answer these questions. As a theoretical physicist, Hawking was equally interested in this question. Does extraterrestrial life exist? First, we need to determine the form of life. We usually think of life as based on carbon atoms. Some speculate that there might be life based on other chemical elements, such as silicon. But within the observable range of the universe, carbon seems to be the most favorable for life, because carbon has the richest chemical properties. The current stability of carbon atoms in the universe indicates a fine-tuning of the physical constants for carbon by the universe. If these constants weren't so exquisite, carbon atoms would easily collapse, and life as we know it on Earth would not exist. Other atoms in the universe don't receive the same special attention as carbon atoms, so the likelihood of their existence is extremely low. From the perspective of life on Earth, there is evidence indicating that life appeared on Earth after 1 billion years. The earliest form of life, cyanobacteria, it took 2.5 billion years for the evolution of multicellular organisms, followed by another billion years to evolve into fish. Subsequent evolution seems to have accelerated. From early mammals to humans, it took about 100 million years. The entire lifespan of Earth is approximately 10 billion years. In other words, life on Earth could develop in the vast 9 billion years of time into the simplest form of life in the universe. Moreover, the early appearance of life on Earth indicates that under suitable conditions, the chance of spontaneous life generation is not small. On a planet with liquid oceans spread across it, given 5 to 10 billion years of time, there is a reasonable probability of accidentally synthesizing RNA, and RNA is the foundation of Earth's first life. You can imagine this situation. It would also occur on other planets with environments similar to Earth. Among the several thousand super-Earths currently observed, 5 are located in their habitable zones. According to this probability, how many planets in the entire Milky Way are located within the habitable zone of their stars? So, the likelihood of life emerging in the universe is extremely high. But the question is, how many of them would evolve into beings similar to humans, and how many possess the ability to discover other intelligent life? Moreover, the birth of humans is still a matter of chance, because it is still uncertain whether intelligence possesses enduring value in the long term. It's still unclear whether intelligence has long-term value, because without the asteroid impact 66 million years ago, intelligent beings like humans wouldn't exist. Dinosaurs would still be around. and after the impact, in the time before humans appeared. During this period, Earth didn't experience another major impact. But looking at Earth's history, every 30 to 60 million years, it undergoes a catastrophic impact. The probability of such impacts exists throughout the Milky Way. Other planets in the Milky Way that have developed life, is there a long enough period without collisions to evolve intelligence? One day, we might be in the Milky Way galaxy, find many life forms, but it's unlikely that we will find intelligent life. There's another possibility beyond the Milky Way. There are many forms of intelligent life, but they are unaware of each other's existence. Even if these civilizations are much more advanced than Earth. Because the scale between galaxies is too vast for the lifespan of life, it's too grand. Our journey is just to the center of the Milky Way. It takes about 1 year, and to reach the neighboring galaxies, it would take tens to hundreds of millions of years, or even billions of years, in many science fiction movies. Future humans and aliens overcome this challenge by bending space to gain extra dimensions, but I believe these are forever impossible, no matter how intelligent life becomes. Because it's determined by the physical laws of the universe, the discovery of intelligent life in this universe finding each other is an extremely improbable event. The last point is, before humanity becomes powerful enough, never release any signals into the universe, and don't respond to any signals that appear to be from extraterrestrial sources. We are always curious about extraterrestrial intelligence, but I don't think so. We cannot impose human perspectives on them. That's very dangerous. Think about what happened after Columbus arrived in the Americas. That scenario is very likely to happen to us. In science fiction, space and time bending are commonplace plot devices. They are used for rapid travel, inaccessible cosmic space, to overcome the problem of cosmic scale. And this behavior would affect time. Many people have generated the idea of time travel from this. So, is time travel possible? A long time ago, the Earth was thought to be flat. It was believed that the straight line was the shortest distance between 2 points. But later it was discovered the Earth is spherical, and its surface is curved. So the surface of the Earth is what we call two-dimensional space. Imagine, if we could dig a hole between the North Pole and the South Pole. The distance between them is 12,742 kilometers. Compared to traveling on the Earth's surface, it would shorten the distance by nearly 8,000 kilometers. This is similar to our universe, which was once thought to be flat, but later proven to be curved by general relativity. The three-dimensional space we live in is another dimension space that we cannot see. It's just that the surface of this sphere is so huge that space in all directions is almost flat. Einstein realized in 1905 the relationship between space and time, and eventually proved it. Time and space as a four-dimensional entity. Every point in spacetime is marked by 4 numbers, defining their position in spacetime. If we want to time travel, we would need a spaceship faster than the speed of light, but according to relativity, the closer the ship's speed is to the speed of light, the more power it would need, until it reaches and exceeds the speed of light. But this would require consuming infinite energy, more than the energy of the entire universe. This is clearly impossible. In 1948, mathematician Kurt Gödel found a solution to the field equations of general relativity, proving that general relativity allows for time travel. This made Einstein uneasy, although he believed time travel was impossible. But this solution had many problems. For example, Gödel's solution couldn't represent our current universe. The cosmological constant in this solution had a considerably large value. In general, we believe it's very small. Because our universe is continually expanding, Gödel's solution only applies to a classical universe model. So can we fold the 2 points in spacetime? to create a wormhole that a spaceship can traverse, and to achieve time travel. Point A represents now. Point B represents million years later. The red line represents the normal path from A to B over time, while the green line is the path through the wormhole. So it could be done in a shorter time. Reaching a moment in the future is what we call time travel. However, when this theory is applied to traveling back in time, paradoxes arise. For example, if you were to kill your grandfather, would you still exist? Therefore, many propose the theory of multiple histories. To explain this paradox, this means that each time you travel to the past, creates an entirely different timeline from the one you originated in. This is what's known as parallel universes. However, Stephen Hawking argued against the existence of multiple universes, because if they did exist, it should be present in the cosmic microwave background radiation, leaving detectable imprints. However, to this day, we haven't discovered these imprints, indicating the non-existence of multiple universes. Even if they do exist, the number of multiple universes is very limited, rather than the infinite possibilities we might imagine, and this would lead to paradoxes. Time travel. The likelihood of it happening at some point in the future is slim. When space-time is curved to a degree, almost sufficient to allow travel back in time, the density and energy of exotic matter would become extremely high, so high that it would be challenging to maintain the wormhole. This implies the existence of a time protective mechanism in the universe, preventing us from traveling back in time. But if general relativity is proven correct, the energy density is positive, making time travel an impossibility. On the contrary, if relativity is not absolutely correct, then time travel would be a kind of correct idea that emerged in our mistaken era. Hawking suggests that certain facts in the universe might be even stranger than the wildest ideas of any science fiction writer. For example, black holes. These are the most peculiar celestial bodies currently known in the universe. The concept of a black hole was proposed before it was confirmed, and the person behind this idea was John Mitchell. He proposed it in 1783, that is, 96 years before Einstein was born. If someone were to shoot a bullet into the sky, then this bullet would eventually decelerate due to gravity and fall back to Earth. But when the speed of this bullet exceeds 11 kilometers per second, the Earth's gravity will no longer be able to pull the bullet back. This is the escape velocity of Earth. Due to varying masses, celestial bodies in the universe differ. The escape velocities are different, but light can easily escape from any celestial body, because its speed is so fast. If there is a celestial body in the universe with a sufficiently large mass and a small enough density, then the escape velocity from its surface would be greater than the speed of light. In other words, not even light can escape from this celestial body. So, we cannot see this celestial body. Mitchell called it a dark star. But his theory was too ahead of its time, and no one delved deeper into the research. Until more than 100 years later, German scientist Carl Sagan rediscovered the dark stars mentioned by Mitchell. Once the mass of celestial bodies in the universe reaches a certain threshold, it will form such a celestial body. Anything that passes through it, including light, will be drawn into it. The radius of this celestial body calculated by Schwarzschild. If the Sun were compressed into a sphere with a radius of 3 kilometers, or if the Earth were compressed to the size of a glass marble with a radius of about 1 centimeter, then the Sun and the Earth would become such magical spheres. This radius is called the Schwarzschild radius. In 1967, John Wheeler referred to this celestial body as a black hole. Hawking was very interested in black holes. He devoted a lot of effort to studying black holes. Around a black hole, there is a boundary called the event horizon. It can be considered as a kind of spacetime boundary. At this point, gravity is just strong enough to prevent light from escaping. It's a bit like paddling a canoe across a river and seeing a big waterfall ahead of you. If you are farther away from the waterfall, then you just need to paddle quickly in the opposite direction to move away. that you can escape. But if you are closer to the waterfall, once you enter the flow of the waterfall, escaping becomes impossible. Similarly, if you are piloting a spaceship, once you enter the event horizon of a black hole, you will be stretched into a spaghetti-like structure, gradually stretched and pulled into the black hole. And the rate of stretching is so rapid, people outside cannot see the scene of you falling in. They would only see your spaceship slowing down, spinning around the black hole until gradually disappearing. When everyone believed that black holes only absorb matter, Hawking discovered that black holes also seem to emit radiation at a constant rate, emitting particles outward. This is Hawking's famous theory of black hole evaporation. The entire universe is filled with pairs of virtual ions and anti-ions. When one of the virtual particles is absorbed by a black hole, the other escapes to infinity. This is the outward radiation exhibited by black holes. Many people wonder where one would end up if they were to traverse a black hole. The center of a black hole is a starting point, formed by the collapse of gravity and mass. This starting point is where all physical theories collapse. Perhaps it could be the most significant discovery in human history. So, what is the significance of the existence of black holes? Assuming our universe's spacetime is entirely flat, it's like finding yourself in an endless desert. Despair sets in as every direction looks the same. However, at this moment, suddenly, an oasis appears in front of you. A pond, perhaps even a camel. Suddenly, the desert seems different. A black hole is like an oasis in the universe, giving us guidance. Black holes are also a crucial part of our understanding of the universe. Hawking also anticipates that future humans can use black holes to comprehend our universe and everything else.
That is all for today's video. Thank you very much for watching this episode. See you in the next time. Bye.